stuff. So first things first, I need to get to my white screen. Hopefully that's working. It is. Okay. In the homework from 14.7, which is where you get to do max and mins and saddle points. There's quite a few questions there. I've reduced it a little bit, try and make your workload at least doable. But there's still going to be a lot of work in this, so I suggest really strongly that after today, even if you've got any time, you get started on these guys. Each question, individual question, can take a fair amount of time as well. So there's a large number of questions and they take time. So you put those together, you're going to be challenged. So what kind of max-min issues are we going to look at? Well, first kind of questions we're going to look at are a group of questions where you've been asked to find the maximum, minimum, or saddle point of a given function f of x, y. And the next group of questions, you're being asked to find max, min, but only maximum and minimums subject to some constraint. So the constraint might be find a maximum and minimum value of x cubed plus y cubed, where x minus 42y always has to equal 7 or something. That would be a good example of a constraint. The third group of questions that we're going to look at today, hopefully we get the time, is find the closest point to a surface. So it's a very specific type of question. So you're going to get a surface like, you know, x cubed minus xy, and you're being asked to find the closest point on that surface to the point 1, 2, 3, or to the origin, or to some other point. So you can imagine you've got a surface and you've got this little point floating out in space. The surface obviously isn't, the point isn't in that surface, but can you imagine you're trying to draw a straight line to that surface and find where on the surface you could get closest. That's a very specific type of question. And then the last group of questions, which I don't think we'll get to today, to be honest, but if we ever do, that'd be great, is going to be the puzzle questions, where you're given a puzzle and you're being asked, to maximize or minimize the surface area or the volume of boxes. Can you remember, God, when did we do that? We did it in 141. Remember boxes with lids and boxes without lids? And we did, where else did we do it? I think you might have done it in Calc 1 as well, where you try to minimize the surface area to make a box, that kind of question. Well, we're going to do the grown-up version of that question, like the ultimate version of it. And that's some of the puzzles in the last part. So, without further ado, I'm going to go straight in, and this is a version of question 3. And this is going to be the max, min, saddle point question. The particular function that we're being asked to do it to is 3x cubed take away 9x plus 9xy squared. Just out of curiosity, did I do that one last time? Because I may have. If it doesn't ring any bells, I'll keep going. Leah, if you're saying something, I can't hear you.
No, sorry, just shouting at the kids.
Oh, shouting at the kids is okay. I like the way you do it quietly. That's a pretty good skill. Okay, so we'll assume then that we haven't done this question. Essentially what we're going to look at here is how to find on this surface what the maximum, the minimum, and or saddle points would look like and where they are. So first stage you're going to do is find the critical numbers, right? So the partial derivative with respect to x. Well, that looks like it's 9x squared, take away 9, take away 9y squared, and we're going to solve that by making it 0. And the partial derivative with respect to y, well, that's a bit easier because that's nothing. That's nothing, and I believe this guy is 18xy equals 0. So we know, question.
So with the partial derivative of x, should that be positive 9y squared?
Yeah, thank you. Don't know where I screwed up on that. Yes, yes. Well caught, Jodie. Right. In this particular one, and you just have to deal with what you're given. You don't get, oh, they all kind of look the same, and so algebraically you kind of solve them all the same way. That's kind of not how this works. In this particular case, I'm going to use substitution. That does work a lot. But in this case, I'm going to focus on this one. I guess I'll give them numbers. I'm going to focus on equation 2, because that one I can solve pretty easily. Would you agree that the only way that's going to happen is in two distinct situations? Won't one of those situations be the x is 0, and won't the other situation get you y equals 0? That seem reasonable? The 18xy equals 0 can only happen at those two places. There isn't another value of x and y that's going to make that happen, right? 0 is x, will make it, and so will y. Now I'm going to do the substitution part. So I'm going to use this guy, I'm going to put it, substitute it into the other equation. So if you take this relationship and you make x 0, you are now looking at solving that, which is much easier to do because it only has one variable. And you can solve this lots of different ways. You can factor it, for instance. I'm just going to do it this way. Would you agree that y could be plus or minus 1? So when x is 0, y has to be plus or negative 1. That means that we're going to get critical numbers of 0, 1, and 0, negative 1. Right, let's go to this fella. If you make y equals 0, here, if you make y equals 0, whoops, here, you get 9x squared, take away 9 equals 0. And can I just cut to the chase? Would you agree that you end up with x being plus or minus 1? And that generates 1, 0, and negative 1, 0. So there are 4 critical numbers. There are 4 places where a local max, a local min, or a saddle point can happen. And that's the only 4 places that they can happen. So that's kind of phase 1 done. Now, for phase 2, we're going to calculate d. Now, d is the second derivative with x times the second derivative with y, take away the second partial derivative of xy being squared, and it's just a piece of magic, but that's the guy that's going to tell what kind of thing is happening here. So I need to do some stuff. I guess I'll do it down here. If this fella is equal to that, then won't the second fella just be 18x? And if the partial derivative with respect to y is 18xy, then won't the partial derivative of y just be 18x? Let me check that. Huh. No reason they should be equal, it's just kind of curious that they are. That's fine. Oh, and I need to know one more thing. Don't I need to know one more partial derivative to be able to get d? Which one have I not done yet?
fxy.
Right. And now I'm about to do the partial derivative of fxy. So I'll take this guy and differentiate it with respect to y, and I get, oh, 18y. Okay. So we are going to use this guy, and this guy up here. And we have 4 different critical numbers to check. Now that's going to take too long for me to do all of them. So I am only going to pick one of them to do, and then you can imagine going through the process of the other 3. Anybody got a preference for which one of these 4 you would like me to test out? Pick one at random then.
0, 1.
0, 1 gets the job, right? So we're going to pick that one. So at 0, 1, won't this second derivative, this fella here, be 0? Agreed? This guy here is 0. And this guy here, what's he going to be? He's going to be 18. Are you happy about the value of these three fellows at the point 0, 1? Are you comfortable that I did it right? Because you know I screw up sometimes. 18 times nothing, 18 times nothing, 18 times 1. So that makes D, right, at the point 0, 1 at least, D is equal to nothing times nothing, take away 18 squared, which makes D negative whatever 18 squared is.
324.
Thank you. Now we use the test. And the test says, if I've got it written here, I think I kept it from last time. Yeah, test says this. If D is less than 0, which it is, agreed? Then won't this definitely not be a local max and min, and is probably going to be a saddle point? Agreed? So to be absolutely certain of it, what you would do is that you would go and plug it into GeoBra, which is what I have done. So let me share that screen. And, oh, well, evidently GeoBra doesn't work well with Zoom. Oh, it kind of moved. Right. Do you see that little guy in that corner there? Can you trust me it's a saddle point, right? Ooh, it definitely doesn't like GeoBra. I'm closing off GeoBra in case it's screwing up my entire system. Right. You can check what I've just done, hopefully a little bit better than I did. I've just been told you can hear each other, but not me. Is that true?
I can hear you.
I can hear you.
Fine.
Okay, I'm
Yeah,
just
I
going
can
to
hear you just
mute
fine.
you all, and that might fix it, right? So now I'm the only person, I guess it could be heard. So if I return back to where we were, according to the test then, since D is negative, we're probably going to have a saddle point, and the answer is we did, believe it or not. So I know it's a saddle point. So we have a saddle point. And it was at x equals 0, y equals 1. And when it's a saddle point, they expect you to put in the z coordinate as well. So if you plug in 0 and 1 here, you get that. So your answer would be saddle point, and you'd write down these coordinates. Now, can you imagine a different point, and I got that D was positive and that the second partial derivative was negative, right? Imagine at one of these points, the D was a positive number and the second derivative at x was negative. What would be the conclusion this time? What does the test say when D is positive and the second partial derivative is negative?
It's a
Maximum, right?
max.
The maximum, right? So it would be a local max. Now, what you would do in your WebAssign is that you would have a little box here called local max. I think it puts a little S in it in case there's more than one. And you would write down, not the coordinate, no, not like this guy here, right? Let's pretend that it was that one, right? You don't plug the coordinates in, which I actually would have preferred. All you tell me is what the value of the function is at that point. So let's say it's 1, 0. at 1, 0, 1, 0, the answer is 3. So you just put in the z coordinate, right? The fxy value. So it's not that you're not getting the answer right, but just so you're clear in your brain what you're being expected to do, you know, how you write the answer into WebAssign. Let me quickly jump to what it looks like in WebAssign. There, that's my version of the question, right? Now, we already found a saddle point, and that's at coordinates, comma, 0, comma, 1, comma, 0. So that's how you would write the answer for a saddle point. On the other hand, we just found a local maximum, and the local maximum had a z coordinate of 3, so you only put 3 in. So do you see it's slightly different format for the answer? You don't write the coordinates for the max and min, only the z value, right? The value of f of xy, which is what the z value is. But for a saddle point, you do a coordinate. And they do give you a clue. Do you see how they say x, y, f? I mean, that's their way of trying to tell you that. So that was a pretty long question. That took us 15 minutes. And I only done one piece of it. But that's how you're going to tackle that particular type of question. And so be aware not to do it Sunday at 10 o'clock, because you'll not get it finished. Even if you say, oh, it's 2, I can do 2, I've done the other 2 in half an hour each. Not this time. Okay, that is our first kind of question where you are given a function and you've been asked to find its max and its min and or its saddle point. So I'm going to zoom using a different term. Okay. This is my next example of max, min, or saddle point. It's actually, in my case, it's question 16. In your case, it may be very similar. Okay, here goes. Partial derivative with respect to x. You know how careless I am, so watch as I go through this. 6x squared, a y squared, a 10x, and a whole load of nothings, right? Got a node, I'm going for it. That doesn't count. That guy gets you what? 2xy. This guy doesn't count, and that guy gets you 2y, and that doesn't count. So we have 2 equations. Now I'm only going to do the beginning of this question, and I'm going to find the critical numbers, because if we can find the critical numbers, can't you do all that other stuff that you need to do to get the D and then eventually decide the answer? So solving for when are these 2 going to be 0 at the same time is the crux of the matter. Now, just looking at equation 1 and equation 2, without going into too much details, which one do you think I have got the best chance of getting a solution of?
2.
You agree it's just got less stuff going on. So focus on the one that looks simpler. So I'm going to focus on this guy and I'm going to try and solve it. Okay, give me something to do algebraically that I could use to solve this equation in 2 variables.
Move the 2y to the other side.
Nope, I know what you're doing, but don't.
Are you just trying to make it equal 0?
Yeah.
Well, if y equals 0, then the whole thing equals 0.
Okay, but to get to that point, wouldn't it be helpful to factor it out?
Well, I mean, I guess you could, but there's only 2 things there.
Right? Now, the advantage of doing that is that can't you now tell that one solution is y equals 0, but don't you also get to find out that there's another solution that you may have just missed if you had moved the 2y over to the other side and I guess divide by 2 and y, which is what I think you would maybe do. And if you just looked at that and say, yeah, I know y is 0, which is true, but would you have known that x is -1? That might have been missed, right, in the mix. So would you agree that there are two distinct ways in which this could be 0? Now, for each of these distinct ways, we are now going to go to equation 1, replace the y by 0 and see what we get, and then replace the x by -1 and we'll see what we get. So let's go with the y equals 0 first. That's going to be 6x squared, that doesn't matter, plus 10x equals 0. Right. So if you're looking at this guy, I would probably pull out 2x as a common factor. And that generates x equals 0 and a rather ugly -5/3. Now you put that together then, doesn't that give me two critical numbers? 0, 0 and -5/3, 0. Are you happy about how I figured those two guys out? Right, now we'll go to the x equals -1, and again we'll plug it into, substitute it into 1, and we'll see what that generates. Well, 6 lots of -1 squared is 6, plus a y squared, plus 10 lots of -1, which is what basically -10 equals 0. That gets me y squared minus 4 equals 0. That gets me y squared equals 4. And that generates plus or minus 2, which I probably should have done as red, but didn't think ahead. So now we have two more places where it works, two more critical numbers. This time it's going to be -1, -2, and the last one's going to be -1, 2. So there are 4 different critical numbers. You might get 2 local max and 2 local min. You might get 4 saddle points, right? It's like 3 saddle points and a local max. Anything is possible, right? In 3D, you can curve surfaces some really weird ways, agreed? All sorts of funny shapes can happen. So there's no predictors here. I don't know what it's going to be until I find it. Now, to find it is the bit I'm skipping. But won't I find the second derivative with respect to y and x and this guy? And basically, won't I find d at that value of x and y, at that value of x and y, at this one and this one? And then I would use my test to decide what happens. So let's just pretend that if I used this answer here, that d was negative, and that the second, let's pretend that d was negative, and the value of the second derivative with respect to x was also negative, right? Just for argument's sake. The fact that d is negative is more important than the second bit. In fact, the fact that d is negative doesn't that make that a saddle point? But you go into GeoBra just to be 100% sure. On the other hand, suppose for this one, d was positive and the second derivative was negative. Now the second derivative with respect to x does become important, because isn't that the decider between local max and local min? D positive makes it a max or a min. It's the value of the second derivative, fxx, that tells you. Would that be a local max or a local min if that was true at that point? D is positive. The second derivative is negative.
Local max.
Right? Local max. Now, when you go and you plug the answer in, for a local max, don't you have to go back to the original function and find out what that is equal to at that point, and that's what you write in the box? But for a saddle point, don't you write down -1, -2, whatever the value of the function is? Right, so you write the answer slightly different format. Are we good? That question took me about 10 minutes, so I'm getting better, but only because I'm cutting out big chunks of the stuff, right? And before I move on to looking at guys with constraints, let me give you a problem. Suppose I have a function f of xy, and I go through the entire process, and one of the critical numbers is that guy, and I evaluate d, and it's 17, and I evaluate the second derivative of x, and it's 10. Local max, local min, saddle point. What have I got?
Local min.
Agreed? At a different point, d is negative 17. The second derivative is still 10. Could happen. What have I got?
Probably a saddle point.
Yeah, and you'll chuck any GeoBra just to do it. The reason I keep saying chuck into GeoBra, just look at the picture. If you see a saddle point, you know it's fine, right? Do you know the one and only time that you don't look at GeoBra to do that is the one time that it's not there, right? It's not a saddle point. You know, that's Murphy's Law, isn't it? You'll do it 10 times in a row and then you get fed up doing it because it's always one. I'll skip it this time and go and darn it, that's the one and only time you shouldn't have skipped. That's Murphy's Law. So trust me, the first time you don't do it, that's probably going to happen to you, right? So just get into the habit. It's good. It's kind of cool to see the picture.
What would it be if it wasn't a saddle point?
It could be anything. It could be a kind of weird ripple in space. It could be some kind of, you know, if you take a surface and give it a kink and bend it back on itself, you could make some weird looking, you know, if you've got a very wrinkled shirt, there's some weird surfaces going on there. It could just be a weird surface. It happens. It just happens. I'll give you an analogy. Do you know if the second derivative is 0, don't you often get a horizontal point of inflection in Calc 1? But isn't it also true that sometimes the second derivative is 0 and you just get a maximum? See, there's no guarantees, you know, that this guarantees a saddle point. Right, 99% of the time, yeah, I'm sure it will be, right? But there's some weird surfaces out there, especially surfaces that have problems with vertical asymptotes or problems with tears in the surface. Can you imagine a surface that's been torn and one bit bends up and the other bit bends down? There's some really issues with what's going on at the point where the tear in the up bit meets the tear in the down bit, right? That's a place where maybe some weird D values could be living as well. So let's start with a constraint question. What does that look like? So I'll take a few seconds if you can hang in with me, and I'll tell you which questions have constraints so you know when you're doing them. That one shouldn't have been there. I took that one out. Never mind. I better not tell you the numbers because there's one of them I took out just to reduce your workload, but evidently it hasn't updated it yet. Okay, so it's easy to tell when there's a constraint. This is my version of question 6 right now. 2x cubed plus y to the 4 add 4, and the constraint will have this bit added. So we are trying to find only maximums and minimums. So don't worry about calculating D. Don't worry about saddle points. We're not going to tackle this question that way, right? Since we know that there is a max or a min to find, all we need to do is find the critical numbers subject to some constraints. In this particular, the constraint is x squared plus y squared less than or equal to 1. In other questions, the constraint is different from that, right? So Step one in these questions is to find the critical numbers. Well, here goes. Partial derivative with respect to x is 6x squared. Partial derivative with respect to y is 4y cubed. If you set these equal to 0, I expect you're going to say, this is easy. I can do this one in my head without really any algebra. Would you agree that there's only one point where both those derivatives are 0? And so we have a critical number, and it's obviously the origin. Can I just say that without any thought? You could figure it out. Okay. Well, what I would do next is I would plug this into the value of the function, and I'd find out that at 0, 0, the answer is 4, which is fine, but we're not finished yet. Because I haven't taken into account the constraint. And now that I've thought about that, there's something I should have done. In this question, the constraint was x squared plus y squared had to be less than or equal to 1, which means you can only use this function provided this is true, right? Would you agree that 0, 0 is definitely inside this constraint? Can you imagine in a different world, this guy here ended up being 1, 1, right? Just for argument's sake. Wouldn't 1, 1 be outside the constraint? Right? It wouldn't be a usable value. And in that case, you wouldn't get any critical numbers at all from the first step. Can you imagine a bigger question where there's 4 critical numbers and 2 are inside the circle and 2 are outside the circle? In that world, won't you only use the 2 that are inside the circle and throw away the other 2 as not usable? Right, so that's one of the little changes. Critical numbers aren't always going to be usable. It depends on what the constraint gives us. Now, the second piece of the puzzle is use the constraint function to change this function. So what do I mean by that? Right. I know that x squared plus y squared is less than or equal to 1, but really we only worry about the boundary of the constraint. You might say about, what about all the other points inside? This has taken care of them, right? This has looked at those guys, so I don't need to look any further. The only place I need to look like is on this fella here. Now, when I look at this question and I put underneath it this guy, what my goal is to do is to turn this function into only having one variable. I either make it a function of x or I make it a function of y. Whatever one I think is going to be the easiest to do. Now, I'll call this guy number 1, I'll call this guy number 2. If I look at equation 1 and I look at equation 2, my mind is saying to me, if you rearrange y squared, you can call it that guy. Agree? And that means then that can't this y squared be put in here and replace the y to the 4 value? So what I now have is 2x cubed plus 1 minus x squared squared. No, that's what I'm going to have to do. Normally when I put solutions on this thing, it will tell me, if it's a awkward one at least, it will tell me at least some clues to where it got the answer, but not this time. So next fella we're going to do, if I can find it, is closest distance to the point, and that's going to be the last one for today because that's going to take a fair chunk of time as well. Oh, that's a nice easy one. That is a nice easy one. Okay, I'm going to do this one. Find the point on the plane x take away y plus z equals 9 that's closest to the point 2, 3, 8. Now, I like that function because this one I have got a fighting chance of showing you what it's like. Can you imagine the point 2, 3, 8 is here? We'll call it P. And can you imagine that the surface, because that's a plane, right, is some big infinite rectangle? Won't there be a point, I'll call it Q, that this point P is closest to that surface compared to any other point I could think? That makes sense. There would be some point on that surface. So how do we actually discover that point? Kind of cool question. Well, I know the equation of the plane, right? And I know this fella. So I create a function. And the function I'm going to create is called the distance function. So you imagine the coordinates of Q being x, y, z. And the coordinates of P are the numbers 2, 3, 8. So the distance function is essentially going to be this guy, right? Well, how do you find the distance between 2 points? Well, it's x minus 2 squared plus y take away 3 squared plus z take away 8 squared. Would you agree that's the distance formula in 3D that you learned way back in Calc 3? Distance formula? Now, that's not the distance function. It could have been, but it's been discovered that that's really ugly and hard to deal with. So the distance function actually is the square of the distance. So f of xy, the distance function, is the square of the square of the d value here. Now, why is that cool? Well, do you know if that distance was 4, won't this distance just be 16? But won't it still be the closest point to the surface? The number that's the smallest square root, isn't it going to be the same place where the number is the smallest square? That's the argument for why that's allowed. But why is this used? Well, square roots are pains in the butt to differentiate. Aren't these a little bit nicer? But there is a second problem. Our function needs to only be in terms of x's and y's. It's going to start off life with x, y's, and z's. So now we have to figure out how to fix this piece to use x's and y's. And that's where this comes in. If you rearrange this, won't z be 9 take away x add y? So our distance function is going to be x minus 2 squared plus y minus 3 squared. But instead of the z, I'll rearrange this to get the z. And it's going to be 9 take away x add y. And now we have the guy that we work with.
Shouldn't there still be a -8 in there?
There is a -8 in there, thank you. Well caught. Z -8. still there. While I'm at it then, I might as well fix it. And basically just get a 1 then, right? We are after the point xy, right? The value of x and y, where this is the smallest it can be, which means we go back to what we did at the start of today. Don't we just need to find critical numbers? And the critical number that gives us the smallest value is the guy we're looking for. Now, there are two ways to approach this. The first one is, couldn't I FOIL all this out and just get a massively big, ugly polynomial with x's and y's? And if that's the way your brain works, then that's fine. Couldn't I just leave it the way it is and differentiate it in situ and just, deal with it? So I'll try it that way. You want to differentiate this lot with respect to x, you get that. If you want to differentiate this guy, don't you get nothing? If you want to differentiate this guy, you get 2 lots of 1 minus x plus y, technically to the power of 1. Do I get anything else out of this one?
Times -1.
Right, so that makes this negative, which means that I can now get 2x take away 4, take away 2, plus a 2x, take away a 2y, and I need to make that 0. Right. And what does that look like then? Well, that and that gets you 4x, take away 2y, I think it's -6. Call that equation 1. I'm going fast, so that means I'm going to make more mistakes, but it's looked good so far. Right, let's hide that for a minute. Do the other one. If you do a, well, I'm not really hiding it, am I? Might as well just keep going then. You do this fella with respect to y now, you're going to get nothing out of that. You're going to get 2 lots of y take away 3 from here, and you're going to get 2 lots of 1 minus x plus y to the power of 1 times 1. So that's not going to do much. This is going to be 2y take away 6 plus 2 take away 2x plus 2y equals 0. Looks like this is going to be 4y take away 2x minus 4 equals 0. That's not minus 4. Yeah.
Should we do roll?
Good. Do roll while I'm finishing this still off. Do you see that we now have 2 equations? I'm going to rearrange them slightly. Isn't that eventually what equation 1 becomes? And isn't that what equation 2 becomes? You agree? Just rearranging that a little bit. Rearranging this a little bit. Right, can we solve that, guy? Sure can. Would you agree there's only one solution? Because it's basically 2 equations and 2 unknowns. It's linear, right? It's going to be one solution. And wouldn't that one solution then be the guy that I'm looking for? So I'm going to try and, God, can I do this quickly enough? That's the question. Let's see if I can do a very fast version of solving this. 2x take away y is 3. 2y take away x is 2. This guy says that y is 3 minus 2x. This says 2 lots of 3 minus 2x take away x is 2. 6 take away 4x take away x is 2. Minus 5x is -4. That makes x 4/5. That makes y 3 take away 4/5. 3 take away 8/5. That makes y 7/5. And then won't z be whatever we get when you got the top, and that would be the coordinates that we're after. And don't quote me on that, because I shot through that and the chances are that I've made a mistake. but the process is correct, right? You solve for X and Y. Once you know X and Y, you return to here to find out what the corresponding Z would be for that X, Y, and that will give you the coordinates of the point. And actually, I've got the right answer according to them next to me. And somewhere, which isn't a surprise, I made a mistake. It's 8/3, 7/3, and 26/3, at least, according to the solutions that are in front of me. Okay, we've covered 3 questions. Max min saddle point, max min with a constraint, closest point question. Anytime you get a closest point question, you'll tackle it this way. Anytime you get a constraint question, you'll tackle it the way we did this one, and obviously the way you do the saddle points. So although you're only getting a little taster, here's one example of how to do it. If you can use that as a template, you should be able to do the other guys. At least that's my hope. But